Everyone, good morning, good afternoon to wherever you may be. As Eddie said, we'll be providing the HSM, and if you actually take a look at the big picture of these two modules together, this is actually the complete package for working on 3D models, whether it be 3D models or prismatic parts. This is actually a very good complete package that you can combine to get the best that you need for this type of work. Now, what I'll be showing in the webinar is I'll be showing 3D iMachining as well as HSM. And when we go to HSM, you'll note what I'll try to do also is show different types of strategies to work on different types of areas, and also make possible suggestions as what type of strategy you should use for different types of situations. Okay, what I'd like to do is actually start off with the part that we see on the screen, and I'll be showing several different parts as we go. Okay, just one moment, please. Okay. Now, if we take a look at the part on the screen itself, you'll note that's a typical 3D part. You can see it being held in the vise. If I take away the vise itself and the stock, you'll see this is the actual part. And this is part actually most of you have already seen in 3D iMachining demonstrations, but I decided to go into it anyway to show some different options that we have today in iMachining 3D. Now, if I were to open up just the operation just for a moment, we'll take a quick look. Of course, we have our target, and I just want to mention again the area of the working area. If I go into define, you'll note I didn't choose any working area, but the only thing that we have here at this moment is where it's automatically set where cut only the rest material. Okay. In this particular case, I'll be using a 12 millimeter end mill with a 0.6 millimeter radius on the tip. And if we go into our technology wizard, you'll note that we'll be going down two steps on the part. It's broken up into two separate steps. Also note, however, that if I were to do this in two separate steps, you would have all the material left over in the middle that still has to be roughed out. And of course, in our technology area, that's where we have the area for the rest rough, whereas the rest rough will automatically step up on the part. Now, the amount that it steps up, the distance that it steps up, is not controlled by a step up factor. No, there is no step up, the amount you step up. It's controlled instead by a scallop, where if you take a look at the diagram on the left-hand side, and it's always a good point out that on every one of these options we have a diagram that shows exactly what it's going to do, so it's a lot easier to understand. If we take a look, what it's actually doing, it's building a surface above the original surface, and from that it's making steps. Now, the shallower the surface itself is, the more steps you'll have. The steeper that surface is, the less steps you'll have. Let's take a quick look at the simulation, and I'll run the simulation right now using Solid Verify. Excuse me. And I'll do it a little slow so we can see exactly what's going on. Now, you'll note that it's going down its first step, and when it finishes its first step, you'll note that it's cleaning up as it's going up on the part itself. Notice it didn't go down to its next step. It went down its first step only, and then it went up to its next step. Now, let me show you exactly why. If it go into the operation itself, you'll note again, if I go into technology, that we have the option over here of each down step, then rest rough. So it first does the down step, then rest rough up to the very top. Then when it finishes that, it goes down to the next down step, and then again roughs up until where this one left off. Now, you'll notice also in my screen right now, this is grayed out. In other words, you only have the option, the very first option. The reason why it's grayed out is if I go back into tool, we have another option over here which I've used called holder collision. When I use holder collision, it automatically closes that area over there and uses the step down first, then rest drop, and then another step down, and then rest drop again. If I were to uncheck holder collision and then go into my technology, you'll note that both fields are now open. Okay, and this, by the way, is very important to make sure that when you're using your tool with the holder, you can get as close as possible as you want without fear that the holder will hit the stock material. Now that we've cleared the material using the iMachining 3D, I decided to continue on with the part using HSM to finish off the part itself. Now, I've used several different types of strategies to do this. My first strategy was as follows. I want to first work on this area over here. Note we have a flat area over here on these two sides, and the rest is actually, as you can see, it's working. We have areas that are relatively steep. We have areas that are relatively shallow. This area over here is not a flat surface. It's actually an angled surface with a little bit of radius. So it's actually also relatively shallow area. Now, we know in the past that constant Z, the option of constant Z, works very well on steep areas, whereas linear works much better on shallow areas. Now, we have the operation of constant Z and linear, but what we have also, if I have to open up the operation, is an option of combining constant Z together with linear, which is exactly what I did in this case. Let's first take a look at the simulation. I'll use the wireframe for this simulation itself. Run my simulation. I'll slow it down a bit, and note it first does the constant Z, and when it finishes the constant Z, you notice it's working on these walls over here. This area did not touch yet. This area over here wasn't touched either. Now it's this area is steeper. It's starting to work on this area as well. The same thing over here. This area is steep. It's working on these areas here as well. Go around the part. It's being done on the entire part. When it finishes those areas, it'll start doing the linear cuts as shown over here. We're about to start it. Let me just finish off over here. Now you can see these areas were done with linear cuts across the part, which are shallower areas. Now you'll note that when I did the linear cuts, it did not touch this area. Now the reason why I did not touch this area is not because of my boundary. The boundary that I gave for the part itself, if I were to actually go back into the operation, the actual boundary, my constraint boundaries, is the entire part. But what I did was as follows. First of all, let's first go into my constant Z passes. If we go into my constant Z passes, you'll note that to keep it on the steep areas, I limited the angles of engagement between 40 and 90 degrees on the part. And if there's anything less than 40 degrees, it won't machine over there, which is obviously these areas over here, this area over here, as well as the floors, because it's less than 40 degrees. Now, if I go into my linear passes, we have it up until 43 degrees, but I also limited the minimum angle of 0.1. Since this is a flat floor, if I just give it a touch of an angle over here, it won't machine this area at all. So actually, instead of making a boundary around that area itself, I just simply said, all right, let's just change the angle to 0.1. Made it a lot easier that way. And this way, it did not work on the floor at all. Now, what I did in my next operation, oh, one more thing I forgot to mention over here, is that in my geometry page, since I'm using a tool of 6 millimeters, a 6 millimeter ball end mill, the radius of that tool is larger than the radius that we have over here, in these corners over here. So to prevent having a sharp turn or sharp corners in that area for the toolpath, in the geometry area, I've added the option of apply fillet. By adding the apply fillet, what that actually does is very simple. It adds a virtual fillet to those corners according to the value that I put in over here. And the value that I put in over here is larger than the value of the tool. So this way I guarantee myself a radius toolpath in that corner over there. Now, let's go into our next operation. My next operation is where I dealt with my floors, my flat floors over here, by simply using the option of horizontal machining. Horizontal machining is specifically made to recognize all the flat floors. What I mean by flat floors is that they're all exactly 0 degrees. Now, also, I've used a tool that has a flat bottom on it. It's actually a bullnose tool, not a ball and mill, because this way, since it's working only on flat areas, and on flat areas like this, I can work with a flat bottom tool. I used a flat bottom tool over here to cover more surface for less tool paths as well. In addition, if we go into our passes area, I've checked off the box here called Detect Core Areas. The reason for that is because if I look at the part itself, you'll note that this floor, these floors over here, can actually be approached from the outside. It doesn't have to be, you don't have to have the tool coming down on it and then working its way out. It can actually be approached from the outside. And this we have now in the option in horizontal machining in our passes called Detect Core Areas. Now, let's take a quick look at the simulation itself. Again, run my simulate, and I'll slow it down and we'll show the tool. You'll see that the tool comes from the outside, working its way in, and the same thing on the other side over here as well. Works from the outside, did not come in from the top, but rather from the outside. Let me just change the color of my tool path over here so it'll make it a little easier to see. Change that very quickly. Again, run the tool path, and you can actually see it now working from the outside going in. Same thing on this side over here as well. Okay. Now, of course, we have to deal with the corners over here. Now, the corner is actually a pretty small corner, and if I were to go into these corners with a small, very small tool, let's say a 2mm radius at the bottom of the tool, in other words, a 4mm ball end mill, I'll still have a lot of material left over here. In other words, I'm asking that small tool to take off a lot of material. And this sometimes can be kind of difficult for that particular type of a tool. So what I've actually done in this particular case is I've broken it down into 2 steps. In my first operation of rest machining, which again is made specifically for removing the excess material on those corners itself, I've used an end mill that was a ball nose mill of 6mm. So it was a 3mm radius on the corner. And in my reference tool, I've told it that since my previous tool, or I should say the fillet that I created over there was a 4mm fillet, as if it was an 8mm tool, I gave it a reference tool of 8.5 to give it a little bit of an overlap. Now this is going to work up until the point, doing exactly what I wanted to do across the part over there, and working over there. Now remember, since I'm working with a tool that's a 6mm end mill, ball end mill, I'm leaving actually here now a radius of 3mm. Now I still have to take this down. But remember now, since it's a larger tool, it worked a lot easier on that material, on that excess material that was over there. If I were to go now into my next operation, I used, in this operation, again, rest machining. This time I used a smaller end mill, took it down a step. And in my reference tool, I used the actual reference tool of the tool that I used in my previous operation, which is the 6mm ball end mill. So it's just going to continue from that point itself. Again, looking at the simulation, you'll see that it works exactly in those areas as well. Okay, Let me start now my next part. And on the next part, actually, let me first close this. I like closing the part first and then opening it, although I can do it the other way also. We'll open my next part. And the next part that you're about to see actually is a sort of a mold. Now, if we take a look at the part itself, you'll see that it's not a big mold, but it's actually something that has several interesting types of surfaces over here. First of all, these floors over here are flat, as well. There's a little bit of a flat area on top over here, and I believe this area over here also is a flat surface. Now, we have a nice area over here that's also kind of shaped, relatively shallow. This area inside over here is also a shallow area. You'll note these walls that we have on the side, they're actually tapered walls, and we have a nice radius, actually a nice fillet going around the entire outside of this part. Now, again, the roughing that I've done on this part, I used the 3D iMachining 3D. Going into the part itself, again, you'll note we have our geometry. I did not create any kind of a working area. We just have the cut-only rest material. In this particular case, this part was done 1 inch, so we have a 3/8 of an inch, which is approximately 9.5 millimeter end mill on the part itself. And it has a little bit of a radius on it as well on the corner. As shown over here, we have a little bit of a corner radius. And if I go into my, also note, I'm using the holder collision. If I go into my technology wizard, again, we have going down 2 steps onto the part. And of course, we have the rest rough working here as well to take off the material as it's going up. Take a quick look at the simulation. I'll use the Solid Verify to simulate the part. You'll see that the tool, I'll slow this down, first does its cut over there, going into that pocketed area, machining it out nicely, as well as this area working its way in. Now note, and let me stop here for a moment, you'll note that it's starting to go up on the part itself. You'll also note that on the part, this area has less steps than this area. This is what the scallop control actually does. Since it's a scallop control, this is a shallower area than this. This is a very steep area, so it doesn't need all these small steps on the surface. It's enough these large steps over here to get the exact results that I need. Continuing on with the simulation, you can see that as well over here. You can see the differences and the steps over here as it starts going up. And we have it going down on the entire part. Again, it went down now to its next step, and then it starts working up on its next step all the way up to the top as well. Now we actually started with the machining on the part. And actually on this part, not only did I use HSM in certain areas, I even used also HSS as well. And even though the webinar is not on HSS, but I'm just going to show you some of the steps that I did over here in HSS, because I think it's really actually very nice the way it's done in HSS in this particular case. What I did actually in my first case was I dealt with the walls around the part. And I actually used the constant Z option in parallel constant Z in HSS to work on these walls itself. Now, let me just go into the operation itself. And you can see I use the parallel cuts constant Z. In my geometry, you can see that my drive surface is the surface going around the walls itself. Note that in these areas over here, there are actual gaps going to its next area. So the way I dealt with that, instead of going across to the next area over there, is if I were to go into my toolpath parameters, I went into sorting, and in sorting itself, I changed my machine by to be as regions. Instead of lanes, which is the default, I changed it to regions, so it actually works in different regions at the time. So instead of continuing on to the next area, when it sees an area over there, sees as a different region, it'll work back and forth in this area, and the same thing as it goes down. So you won't have that jumps as it goes to the next surface. Instead, it'll work on this surface over here. When it gets down to the very bottom, then this area will continue working on as one continuous surface. Let's take a look at the simulation itself. And it's a very, very simple but clean toolpath around the part. Let's take a look. I'll make it go a little quicker. You can see that these areas, there are very little jumps going around on the part itself. When it went to this area over here, it didn't go across to this area, but instead it actually continued working. And on the bottom over here, this is the area itself just continued working around on the bottom itself. And this was done simply with HSS. Okay, I thought it was actually a very nice toolpath, so I threw that in here as well. Now, let's continue, however, with the HSM. Now, in the HSM, first I dealt with the flat floors in this particular case, and if I take a look at the operation itself, we have horizontal machining. We have a tool that has a flat bottom to it with a little bit of a radius. In our constraint boundaries, I decided to give it a boundary, even though I didn't really have to, but I decided to give it a boundary anyway, of working between the outside. Take a look at the bottom over here, at the top view. We have between the outside and this area. Actually, the reason why is because this area over here is also flat, but I did not want it to work in that area itself. So I just limited it to those areas over there, which by doing a simple boundary name. Note again my passes. I have detect core areas so that I can go in from the outside on those areas as well. And just take a quick look at the simulation itself. You'll see that it works only on those flat areas as shown over here. These areas over here and those areas there as well. And this is, as I said, picked up automatically from the option of horizontal machining. Now, let me start talking about our next operation that I want to show you in HSM. The next operation in HSM that I'd like to show you is actually something called, excuse me, 3D constant step over. If I were to open up the operation itself, first, before I actually talk about the operation, I want to actually look at these surfaces over here. Note these surfaces over here, as well as the area inside over there, these surfaces over here can be done very nicely in linear. However, what I've decided over here is, look, you know what I'd like to do? I'd like to actually have the tool, instead of going linear back and forth on the part, I'd actually have like the tool work according to the shape of that particular area. Now, this is, many people I know that work in molds, for example, they actually like to have the shape of the actual toolpath itself going according to the shape of the area itself. So for this, I've actually used the option of 3D constant step over. Now, the constant step over means as follows. It actually combines, if I go into passage, you'll note that at the horizontal step over, and we have a vertical step over. What this actually does, it actually combines the two to give an even step over no matter what the surface condition actually is. So if I have them both set at the same number, even if it goes down from the top view, you'll note that the distance in these areas between step and step will be the exact same as it goes around the part itself. Let's take a quick look at the simulation. And you'll note with the toolpath, there's actually, let me actually speed it up just a little bit. You'll actually see it's actually taking the shape of that particular area as shown over here, which gives us a really nice, clean toolpath on that surface. Now, I did large step overs just so that you can actually see the toolpath itself. Obviously, when you're working on a real mold, the toolpaths, the step overs will be smaller, so you can get a nice, smooth surface as well. Taking a look at the very top of the part, from the top view, you can actually see the real toolpath that we're getting along the part itself. Okay, now the same was also done in this next operation over here, sorry, in the previous operation, doing this floor surface over there as well. Now, we're just about finished with the part, but one thing again I had to show you was how nicely the fillet was actually done on the part. If I go to my next operation, this was actually done using HSS. And if I go into my HSS operation, you'll note I use the option of morph between two boundary curves, whereas my first drive surface was actually the radius around the part itself, as shown over here. The start edge was the edge at the very bottom, as shown on the part, at the very edge of the radius, and the end edge curve was the one on the top. Now, taking a look at the simulation itself, and I did actually a pretty big step over it, so it makes it a little easier to see what's going on. You'll see it's actually working more between the two curves, keeping a nice even step in between each area over here without it actually jumping up at any point. There are no gaps in here. It actually did a nice smooth cut around that fillet itself. This is probably one of the best ways I've seen that we have for machining fillets. Okay, now that I've finished this part, let's take a part that's a little larger. I'll close the part that we have on our screen. And we'll open up our next part. No, actually, I want to do another part. This part everyone knows, but I actually want to do a part that's actually larger. My mistake for opening that one, sorry. There we go. Okay. Taking a look at this part, you can actually see this is a nice mold. By the way, this is a part that we actually did cut. We have actually the part here in our office. This part itself is, you note that we can have the roughing done on the outside over here. You can see all the different shapes that we have in this part. It's actually a pretty interesting part. Now, what I've done here inside the iMachining is actually I've broken it down into two different tools. If I actually open up the first operation, you'll see that we have our target. My tool is a relatively large tool, a 20 millimeter end mill on the part itself. And of course, we have our step downs as shown over here, our technology. I also have it over here at each step down, then the rest rough. Let's take a quick look at the simulation itself. I'll use the Solid Verify for the simulation. Note also, by the way, the part actually loads very quickly, even though it's a large part. Now, let's continue with the simulation. You'll note it's taking very large cut because it can, and then stepping up. Now, over here in this particular case, I have pretty large, a large scallop because I want to take care of the most of the material that I can with this tool. I just want to get most of the material out of the way because there are areas that I need to get into with a smaller end mill for the roughing. But I've cleaned away most of the material already with this larger end mill. Now, so what I did in my next operation is I've actually saved and copied the previous operation, but all I did was go into my tool and change the end mill that I have to a bull end mill with a 12 millimeter bull end mill with a nice radius on the corner itself, a 4 millimeter radius. Again, in our technology, we have the exact same thing we had before. This time, however, our scallops are smaller than in the previous operation. Now, let's take a look again at the simulation of this part. Again, I'll use Solid Verify to simulate it. You'll note that the tool is only working in the areas where the previous tool did not work. It is not working anywhere on the outside, no air cuts over here. Everything is being done exactly on the part itself. Again, remember, in our area of machining, a working area, we have it's automatically checked off that cut only rest material. So that makes it recognize only the material that's left over from previous operations. If it's a complete stock, it'll work on the complete stock. If something was machined away, just as in this case, it's only machining the areas that were left over as shown over here. We'll let the simulation finish until the very end. Actually speed it up just a touch, and you can see that it only worked in those areas very nicely, not touching any of these other areas at all. Now we go into our HSM. Now, the way many people like to work on molds, since on molds they need a really nice smooth surface, what they'll do many times is simply work with HSM first as a semi-finish, leaving a little bit of material left over on the part itself for a finish cut, leaving a minimal amount of material on the part itself, also leaving for a lot less varies in pressure on the tool itself, because the surface that's left over after the finish, after the semi-finish, is a lot smoother than the rough cut itself. If I have to go into this operation over here, for example, you'll note that we did a simple linear operation. Sorry, wrong operation. If I go into the HSM, you'll note that we did a simple linear machining on the entire part. If I go into my passes, you'll note that we're leaving 0.2 millimeters of material left on the surface itself. If I were to run my simulation now, you'll note, and I'd actually do it now just regular host CAD, you'll see that it's going across the entire part, leaving 0.2 millimeters. Now, at this point, I'm not really concerned with the shape of the different surfaces, for the simple reason that this is not the actual finished cut. So this is not what the what the final result will look like on the part itself. Okay, so it did its linear cuts in these areas itself. But again, as I said, it left the 0.2 millimeters. Now, of course, I want to do also a rest machining also here based on what we call giving it a semi-finish as well. And this time using a 10 millimeter ball end mill, giving it a reference tool of 12 millimeters, giving it a radius of 6, which is larger than the that we had, so it can actually work well in those corners. Again, looking at the simulation, you'll see that it's working exactly where the rest machining should be working, just on the corners itself as we go around the part. Now, in our next operation, I've actually used a different type of strategy. Now, if I'm taking actually a look at the part, I'd like to actually have areas which can work constant Z to work constant Z, but the rest of the areas to do something that's very similar to a 3D constant step over. For that, we have an operation in HSM called hybrid constant Z, where it actually works constant Z on the steep areas, but when it starts going off into areas that are angled off, it'll actually start doing something that's very similar to the 3D constant step over, working according to the shape of that particular area. Let's just look at the simulation that we have on the part itself. Taking a look at the top view itself over here, I'll run the simulation. Let me just move this over to the side. You can see the constant Z tool passes as it's going on the part itself. Let me actually speed this up a little. But you'll note that in certain areas, all of a sudden, it'll start working. Note that this area, which is flat, was not machined at the very beginning, but then was machined at the very end. Now, you'll note that even the flat areas were machined. Normally, constant Z does not do that. Constant Z does not work on flat areas. However, the hybrid constant Z takes those areas and treats it like a 3D constant step over. In that area itself over there, you'll note in these areas over here as well. If I would take a look from the top of the part, you'll note in here as well, it treated that area as if it was a 3D constant step over, each according to the shape of that particular surface. Same thing over here in the middle. This is actually a very good solution, one-step solution, I should say, for doing parts such as molds, such as we see over here. I find it actually a pretty powerful operation, and we like working with it on these type of parts. It gives you that really nice finish at the end, exactly the way you need for each surface over here. Now, I'd like to actually load one more part. Now, the next part I'm going to load, I'm not going to go through all the operations that I did over there, and it's actually a pretty large part, but I just want to show you some of the manipulations that I've actually done on the part itself. Opening up the part. It's a part some of you may recognize. I think it was even actually used as the intro picture for this webinar, is this machine, this engine block as shown over here. Now, it's actually a pretty large, heavy part itself. If I were to actually show you what I've done here for stock material, we've actually had the stock material where the outside is more or less like the shape of the outside part itself, so we can have a minimal amount of material to take off as we're working on the part itself. Now, note what I'd like to do when I start working with the iMachining, with the iMachining 3D, is to work only in this area when I'm looking from the top, and then in the holes when I'm working on the side. Let's take a look at the operations themselves. Going into the operations, first I've done some simple face mill operations to take off material on top, on the sides, and all the sides that I can think of. Okay. Now, if I go into my iMachining, my first operation of iMachining, you'll note in my working area, this time I did give it a working area. If I were to take a top view of the part itself, you'll see that my working area is this area itself. So now actually, anything outside over there, it won't machine. It'll only work within that area. But also remember that we still have the option over here checked off, called cut only the rest material. Now, remember that our stock material, if we were to take again a look at the stock itself, you'll see our stock material is going off at an angle over here. So in these areas, even though my boundary is up until this line over there, as shown over there, even though it's up until that line over there, since there's no material in this area over here, it'll only machine from this point in. That's because we had that's because it's automatically checked at the rest material only. Let's take a quick look at the simulation of this part. And I'll use the simulation of Solid Verify. You'll also note that it's a large part. The Solid Verify loads actually pretty quickly on the part itself. There we go. Running my simulation, you'll note that's working from the outside only in the areas where it needed to. In other words, it didn't work anywhere really past the part itself, only within the areas that it really had to work. And because I gave it a working area instead of the entire part, it's only working inside that area itself. Okay, let's run it to the very end until it finishes the simulation. And you can see it worked exactly the way I wanted it to work. Now, my next iMachining operation in this particular case was working, and let's actually get rid of the stock over here so we can see the part a little better. My next operation over here was working in these holes over here, as well as another operation working in these areas over here, again using iMachining. Now, in this particular case, I used two different operations for iMachining. My first one was using a tool. And take a quick look at the tool itself. We were sticking out of the holder by 100 millimeters, a 25 millimeter end mill, sticking out 100 millimeters from the end mill itself. So, but I actually have to go much deeper with the part itself, into the part itself. Taking a look at the simulation, and again, I'll use the option of Solid Verify to simulate the part. You'll note that the tool is going down up until a specific depth only. Because I limited it to a specific depth to work only there. Now, in my next operation, and I'll just show you the simulation, we have a much longer tool. So the next operation will only work from that area down. So I basically broke this up into two different operations. This way I don't need one large tool for that. I can actually use a shorter tool in the very beginning, and then the longer tool at the very end. Now, I did the same thing, obviously, for both sides. Now, let's go into my HSM operations now. If I go into my operations that I did over here in HSM, there are two possible ways I can do it. Actually, the first way, if looking from the top view, was just doing a combined constant Z with linear inside this area itself. If I were just to run the simulation on the part, I'll use this time linear. You'll see it's working on the entire part, on all the lines over there as well. Now, taking, however, a closer look at the part itself, what we'll see in the part is very simple. Let me just get rid of the simulation itself. What I can do, since I'm holding it on a fifth axis machine, I can actually tilt it this way, just like it did in the holes, and then these areas over here, these areas are actually flat, as well as these areas over here, and the same thing will happen when I turn it this way. So what I did was, I did very simple. Instead of actually doing a constant Z on these walls over here, which are many passes, I used the option of horizontal on these floors itself, as shown over here. Running the simulation, you'll see that the tool is only working on the flat areas, and the distance between each step is much wider because it can do it with larger step overs. So therefore, we can have less passes on the part itself, also working quicker because of that. The same thing was done for my next operation over here, working, however, on the other side over here, on the flip side over here. Again, using the option of horizontal. Now, to work in this area, of course, I use the exact same operation that I did over here, but what I did was, if I go into my constraint boundaries, you'll note that my constraint boundaries in this particular case, I still have the entire part outside, including the walls. But what I did was, to make sure that it didn't work on the walls itself. I didn't want to start messing around with the parts, starting finding each area over there. I just used the exact same working area that I did before. But what I did was, in my constant Z passes, I actually activated my edit passes. Whereas in the edit passes, I have it at auto update stock, so it'll automatically work on the areas where there's stock to be worked on. Okay? Where there's no stock left over, it won't work there at all. So in other words, these areas, since they were machined already, it won't work on those surfaces by using this option. I even gave a little bit of an over thickness of a negative value just to make sure, in case there were, in case the part was scalloped, a little, you know, like sometimes you have a small, what we call tolerance was actually is exactly on that 0 area. Sometimes we'll actually do passes on it. So what I did was, in the edit passes, I just give a little bit of an over thickness, so this way it definitely won't work in those areas. Let's take a look at the simulation. You'll see that in the simulation itself, it's only working on this area over here, on the areas where it needs to work on. Let's actually let it run until the very end. You'll see that the tool pass is only on these areas itself. Note that these walls over here will not be machined. Okay, let's just run. You have to go until the end over there, and you can see that skipping these areas altogether, not working there at all, just in the middle of the part. So what we basically saw is that different ways to manipulate HSM, this ways to use HSM, besides the iMachining 3D, which is the best way to take off the excess material, all the rough material that needs to be taken off. The HSM, we've actually used different types of strategies to work on different types of surfaces, and we've shown different ways that we can use the HSM to do that as well. Okay, I am basically finished, and Eddie, we're ready for questions.